Okay, so the universe is doomed. Cool, right? Number 10. Big Rip. The night sky looks the same tonight as it did last year. Same constellations, same stillness. But that stillness is a lie. Every galaxy in the observable universe is drifting away from every other galaxy. The force behind that drift is something we still don't fully understand. We call it dark energy. Right now, it pushes space apart at a steady rate. That's manageable. What isn't manageable is the possibility that this push gets stronger over time. Some models call this phantom dark energy. If it exists, the acceleration doesn't just continue. It runs away, and it follows a schedule. First, the clusters of galaxies lose their grip on each other and drift apart until the night sky goes completely empty. Then, individual solar systems fail. Stars peel away from one another. Planets leave their suns. In the final stretch, the forces holding matter together get overwhelmed. Electrons unstick from atoms. Atomic nuclei crack open. Everything that ever was gets shredded down to nothing. Astronomers test this by measuring distant supernovae and the faint afterglow of the Big Bang. So far, the best data point to a steady push, not a runaway one. That makes this ending unlikely, not impossible. We're still figuring out what dark energy actually is, and the answer could change the whole picture. Number 9. Heat death. Every fire burns out eventually. Every engine runs down. That's not poetry. That's the second law of thermodynamics, and it applies to the entire universe. Energy flows from hot to cold. Stars radiate their heat into empty space. Over time, the differences that let things happen start to disappear. Temperature gradients flatten, chemical reactions slow, the basic machinery of life winds down, everything reaches the same low temperature. Nothing can do work anymore. This doesn't happen fast. The last stars won't burn out for another 100 trillion years. After that, the universe belongs to black holes. Even they slowly leak away through quantum radiation over timescales that make 1 trillion years feel like a heartbeat. We're talking Google years. 10 to the power of 100. At the end, there's nothing left but a thin, cold soup of particles and low-energy photons drifting through an ever-expanding darkness. No collisions, no reactions, no change, just silence, forever. Most models with current data point to this outcome. It's the default ending if nothing else intervenes. The universe doesn't go out screaming. It just stops caring. Number 8. Big Crunch. For most of the 20th century, the big question in cosmology was simple. Will gravity win? If there's enough matter in the universe, expansion should eventually slow down, stop, and reverse. Galaxies that spent billions of years flying apart would start falling back toward each other. Slowly at first, then faster. The late universe becomes a furnace. Galaxies collide and merge into a single roaring sea of light and heat. Stars ignite in violent bursts. Planets vaporize. Temperatures climb until matter gets crushed into forms we don't have names for. In some models, the collapse reaches a singularity and time itself ends. In others, quantum effects step in at extreme density and trigger a rebound. A new expansion from the ashes. That version is called the Big Bounce, and we'll get to it later. Observations since 1998 shifted the consensus away from collapse. The universe isn't just expanding, it's accelerating. That makes a crunch less likely under most current models, but it doesn't rule it out. If dark energy weakens or changes, sign over time, gravity could still win. The deciding numbers are small, subtle, and still being measured. Astronomers won't settle this for at least another decade. Until then, the crunch stays on the table. A hot, violent ending where the universe takes back everything it made. Number 7. Vacuum decay. Imagine you're standing on what feels like solid ground, and the ground itself changes its mind about what solid means. Quantum fields fill all of space. The Higgs field is one of them, and there's a problem with it. The math suggests it might not be sitting at the lowest possible energy state. It might be perched in a shallow valley with a deeper one below it. Stable enough for now, but not forever. If some tiny quantum event nudges a point in space over that barrier, a bubble of new physics forms. Inside the bubble, the fundamental constants are different. Atoms might not hold together, chemistry might not work, and the bubble expands at nearly the speed of light without making a sound. You wouldn't see it coming. No warning, no signal, no time to react. One moment the rules work, the next moment they don't. Physicists actually take this seriously. Teams have simulated the bubble process in labs using ultra-cold atoms and quantum machines. Not to prove we're doomed, but to learn how these transitions work. The expected lifetime of our vacuum, if it's metastable at all, is astronomically longer than the current age of the universe. We're probably fine, but the fact that probably is the best answer physics can give you about whether reality might spontaneously rewrite itself is what keeps the question open. Number 6. Brain-world collision. String theory introduces an idea that sounds like science fiction but gets taken seriously in theoretical physics departments. Our entire universe might be a four-dimensional sheet called a brain, floating inside a larger space we can't see or touch, and there might be other sheets nearby. If two brains collide, the result is nothing like a car crash. It's more like two ocean waves slamming into each other and rewriting the ocean. The impact would compress and heat everything on our sheet simultaneously. Galaxies would be destroyed. Space itself could be reshaped in ways we don't have the physics to predict. Scientists have looked for signs of an ancient collision in the cosmic microwave background, unusual temperature patterns, and odd gravitational wave signatures. They've found hints, cold spots, anomalies, but nothing definitive. Most researchers call this speculative. The math is elegant, the evidence is thin, but if it happened in our past, it might explain how our universe got started, and if it happens in our future, nothing we know would help. Number 5. Big bounce. Most endings on this list happen once. This one happens over and over. The big bounce says the universe doesn't just collapse, it hits bottom and springs back. Contraction squeezes everything to unimaginable density. And then quantum effects we're only beginning to understand kick in and reverse the fall. The framework behind this is called loop quantum cosmology. In classical physics, a collapsing universe hits a singularity where density goes infinite and the equations break. Loop quantum cosmology says that doesn't happen. At the smallest scale physics can describe, a repulsive force emerges that overwhelms gravity. The universe rebounds. In late 2025, physicist Henry Tai and collaborators published models showing something uncomfortable. If dark energy isn't a fixed constant but changes over time, it could eventually turn negative. Expansion slows, stops, and reverses. Their models put the crunch roughly 20 billion years from now. Think about what that means. Every civilization, every planet, every record of anything that ever happened gets compressed to a point and erased. Then a new universe inflates from the wreckage. New stars, new planets, maybe new life. None of it remembering what came before. Scientists look for evidence in the cosmic microwave background and search for scars from a previous bounce. So far, nothing conclusive. But the possibility that all of this has happened before and that everything you know is just the latest draft in an infinite series is a thought that sits with you. Number 4. Proton decay. Pick up a rock. Feel how solid it is. The atoms in that rock have been around since before the Earth formed. They were forged in the cores of dead stars billions of years ago. They feel permanent. They might not be. Grand unified theories predict that protons aren't truly stable. So these are the theories that try to tie all the fundamental forces together, and they say that given enough time, protons will break apart into lighter particles and radiation. Not in a billion years, not in a trillion. The lower limit on a proton's half-life is at least 10 to the 34th power. That's a trillion times the current age of the universe. Experiments at Super Kamiokande in Japan have been waiting for this since the 1990s. Thousands of tons of ultra-pure water sitting deep underground, surrounded by detectors, all watching for a single flash that says one proton just died. So far nothing. But if protons do decay, then everything made of ordinary matter has an expiration date. Stars, planets, white dwarfs, neutron stars. All of it slowly crumbles as protons vanish one by one. What's left isn't dramatic. No explosion, no flash, just a thin bath of photons and neutrinos drifting through an ever-expanding void. The universe doesn't crash. It quietly empties out, like a room where people leave one at a time until nobody notices the last person is gone. Number 3. Iron Star. Here's one that doesn't get talked about enough, and it might be the strangest ending on this list. Iron 56 is the most stable atomic nucleus in existence. It sits at the very bottom of the nuclear binding energy curve. That means if you gave nature unlimited time, everything would eventually become iron. Lighter elements fuse toward it. Heavier elements decay toward it. The destination is already written into the physics. The mechanism is quantum tunneling. Even at temperatures near absolute zero, particles can occasionally pass through energy barriers that should be impossible to cross. The odds are vanishingly small per event, but the timescale isn't a billion or a trillion years. It's 10 to the power of 1500. Write that number out and it would fill pages. Freeman Dyson worked through this in a 1979 paper on the far future of an open universe. He showed that if protons don't decay, the stellar remnants left behind after all the stars die will slowly undergo tunneling reactions that convert their cores to iron. White dwarfs, neutron stars, every cold, dead object in the cosmos all slowly turning into iron from the inside out. The result is an iron star, a cold, dark ball of the most stable element there is. But even those don't last. Diese Aktionen. On even more absurd timescales, the iron masses tunnel into black holes, and the black holes evaporate through Hawking radiation. Nothing remains, not a violent death, cosmic rust, working on a clock so slow that the entire current age of the universe is less than a camera flash compared to it. Everything solid becomes iron, everything iron becomes nothing, and nobody is left to notice. Number 2. Boltzmann brain. Open your eyes. You remember waking up this morning, eating breakfast, a childhood full of memories, a sky full of stars. But none of it happened. You're a brain that flickered into existence from random particle collisions in an empty void. You'll dissolve back into nothing before you finish this thought. That sounds absurd. It's also mathematically rigorous, and real physicists lose sleep over it. In a universe that lasts forever and eventually reaches thermal equilibrium, which is the heat death we talked about earlier, random statistical fluctuations have to happen. It's not a question of if, just when. And here's where it gets disturbing. It's vastly more likely for random particles to accidentally assemble a single conscious brain with false memories than for an entire ordered universe with billions of galaxies and biological evolution to emerge from scratch. If the universe is eternal, Boltzmann brains would outnumber real observers by an incomprehensible margin. And if most observers are Boltzmann brains, then statistically you should be one too. Physicists like Sean Carroll at Johns Hopkins use this idea as a stress test for cosmological models. If your model predicts more Boltzmann brains than real observers, your model is probably broken. That means the universe either can't last forever, or we're missing something fundamental about how quantum fluctuations work. What keeps this problem alive in serious research isn't the idea that you might be a Boltzmann brain. It's that our best physics can't definitively say you aren't. Number 1. Simulation shutdown. Flip a light switch. The room goes dark. You didn't break the bulb or cut the wire. You just turned it off from the outside. The simulation hypothesis says something like that could happen to reality itself. If our universe is a computation, and the laws of physics are code, and the constants are parameters, then the ending doesn't have to be physical. It doesn't need a crunch or a rip or a freeze. Something on the outside just stops running the program. Computer scientists and philosophers have built formal frameworks around this idea. It isn't just speculation. Researchers have proposed real tests, looking for maximum resolution limits in the universe and searching for unexpected patterns in particle physics that might reveal a hidden grid underneath what looks like continuous space. Critics push back hard. Some mathematical work shows that simulation questions might be formally unresolvable. You can't prove you're in one from the inside. Others point out that the energy needed to simulate an entire universe would be absurd even for a civilization far beyond ours. Every other ending on this list is physics. This one is administration. The universe doesn't die, it gets shut down. And the question that sticks isn't whether it's true. It's whether it changes anything about how you spend the time you've got.